So does anyone know how to describe a charged particle in an electromagnetic field? What is the equation? You're all veterans of classical electrodynamics, so you should know.
In terms of force or potentials?
In terms of force, what's the name of that force?
Oh, that's just the Lorentz law, Lorentz force.
Lorentz law, exactly. So the Lorentz law, it tells me if I take a charged particle and put it in an electromagnetic field, the force on a charged particle in an electromagnetic field is given by the Lorentz law. Okay, this is a law of nature, just as Newton's law is a law of nature. And that's given by the force on the particle is the charge times the velocity across the magnetic field divided by the speed of light plus the electric field. Okay?
So is this Gaussian units?
Yes.
Oh, okay.
Otherwise, I think so, yeah. I think I don't want to worry about 4 pi, epsilon, blah, blah, and all those kind of stuff. Yeah. All right? So now, according to Newton's law, this F is equal to the mass of the particle times the acceleration, right? So we can now express this equation of motion in terms of like this. And on the other side, instead of E and B, I'm going to put A and phi. And also I'm going to assume that we are dealing with electrostatic fields. Sorry, not electrostatic. We are dealing with static fields, okay? That our magnetic fields and our electric fields do not, depend on time. So I'm going to essentially, ignore the time derivative in the definition of E. Remember that there's a time derivative here. Okay, somebody's calling me. Just 1 second, okay? Hey, Amina, is this a emergency? I'm in a class right now, so.
Okay. No, it's not. It's not.
Okay, let me call you back after, okay?
Of course.
Okay,
Of course.
okay, no worries, bye. Sorry about that. Yeah. All right, so if I go back, then we see that there is this, there is this term. There's this term, right? So we are going to assume that A is time independent, therefore this term will drop out, okay? We can keep that, but we won't need it for our purposes, okay? I'm just going to simplify life a little bit. So then our equation of motion becomes V divided by C cross B becomes curl of A, and then E becomes minus gradient of phi, okay? So what I've done is that I'm just replacing B and E by the gauge potentials, okay? Now, although I have ignored, A, the time derivative of A, we can say that if I had taken the total time derivative of A, then I would have two terms. One would be the partial derivative of A with respect to time. Another would be the dx by dt d by well, let me use a different notation, dotted with the gradient with the del operator acting on A. Okay, I'm just using the law of the chain rule, right? Yeah.
Sir, where does Q by C comes from? There are two C's in the first equation.
Oh yeah, so there should be only one C. Yeah, good. Okay. Or no, the C should be inside. Yeah. No, because let me see, what was the definition of E has, okay, yeah, you're right. My bad. Okay. Right. Yeah, I think the Lorentz force has only yeah, I think it's correct. Yeah, okay. So this is 0. Now, what we can do is we can then use the vector identity, the vector calculus identity, that the V cross the curl of A is equal to the gradient of V dot A minus the directional derivative along V of A, and recognize that this object is nothing but minus of this object, and therefore, of the two terms that are generated from this, one can be replaced by the total time derivative. And therefore, m dv by dt is going to be q minus grad of phi minus 1 over c dA by dt plus 1 over c gradient of v dot A. Okay, so this is the form of the equation of motion written in terms of A.